Okay, in today's lecture, we want to talk about an application of sinusoidal functions that we see in electrical engineering, and that is AC voltage and current. So in order to do this, we'll have to do a couple of things, including a quick review of complex numbers and complex number math. So what is an AC voltage and current? Most of you know that it's the kind of current and voltage that you have in your house. You know that in the United States, the common frequency for a household voltage and current is 60 hertz and 110 or 220 volts. So you probably heard all of those words, and what I want to do now is connect those to some definitions and kind of get you introduced to how in the electrical engineering field we talk about and work with AC currents and voltages. So our previous analysis was for DC or constant current and voltages, and all of the laws, all of the circuits laws that we used, like Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law, apply for currents and voltages independent of their functional form. So whether you have constant currents and voltages or whether you have AC currents and voltages, the laws all still apply. Now, in many applications, including power in your household, voltages and currents consist of an AC or an alternating current signal. Now, alternating current just says current for historical reasons, and so that's how we got the abbreviation AC. But actually, what that means is that every current and voltage in the system has a mathematical form of a single frequency cosine wave. So this single frequency cosine wave will have an amplitude, a frequency, and a phase shift similar to the one we saw in a previous lecture. So here is an expression for voltage as a function of time for an AC voltage. And in this particular expression, we have some amplitude or magnitude, V sub 0. Then we have the cosine of omega t, where omega is a frequency in radians per second. And then we may or may not have a phase shift phi. So for a given AC circuit, the frequency omega is always a constant, and it's the same throughout the circuit. So we don't have, unless you get into something really exotic, we do not have, circuits do not shift the frequency of the signal that's going through them. There are, later on, if you get into the pulse power area or some other areas, there are circuits that you can build that do introduce a change in frequency. But for what we're working with now, an AC circuit always has just a single frequency shared by all, the same for all currents and voltages. And that's going to end up being important when you get to circuits and you deal with how to analyze AC circuits. All right, it's important in order to understand AC circuits, we're going to go back and review some things from earlier in the semester, including Euler's relationship and the relationship between sine, cosine, and complex numbers. And the reason to do this is, as you know, if you've worked with trigonometric functions before, when you have sine and cosine functions and you're trying to do addition, subtraction, or other mathematical operations, it turns out that that's very hard to do, and you have to use pretty elaborate things sometimes like double angle formula and trig identities. So equations as a general rule are hard to solve with trigonometric functions. So one of the reasons to look at the relationship between trigonometric functions and exponential functions is that exponential functions tend to be very easy to work with and very easy to solve. So in solving AC circuits, what's done is a transformation between working with the cosine function and working with the exponential function. And that's the reason for this review of Euler's relation and complex numbers. All right, so if you recall, we have a complex plane. The vertical axis is the imaginary axis. The horizontal axis is the real axis. And in general, a complex number will have a real component, which is shown on this figure as A, and an imaginary component, which is shown on this figure as B. And then the number can be represented graphically by drawing an arrow from the origin of the complex plane to the point that's represented by the complex number with real part A and imaginary part B. So we refer to A as the real part of the complex number. We refer to B as the imaginary part of the complex number. The complex number itself is A plus BI, or in electrical engineering, we would often write that as A plus JB. Complex numbers are often represented graphically on the complex plane. What's not shown here is that the angle that the complex number forms with the real axis is measured from the real axis to the line that denotes the complex number. Okay, so here's a different figure that illustrates that. So the notation is a little bit different here. We have the complex number denoted as 0, the x component, or the real component, denoted as x, and the imaginary component denoted as y. And so our complex number has a length of r, or z, magnitude of z, and it has an angle that it forms with the real axis of phi. So r is the length or the magnitude of the complex number, and phi is referred to as the phase. Now, the complex conjugate of a complex number is basically the same thing, except the imaginary component, the sign, is changed. So you can see down here we have x minus iy. We have a minus sign here, and all that does is move the complex number to this quadrant of the complex plane. Notice that the magnitude of the complex number r remains the same, but the phase angle now is a negative phi compared with a positive phi. So phi is measured in a counterclockwise direction from the real axis. So if we measure it in a clockwise direction, then we have a negative phase angle. Okay, also notice that we can express x and y in terms of r and phi. So x is r cosine phi and y is r sine phi. That's just from some trig. All right, what Euler's formula does is it relates a complex number in polar form to a complex number in rectangular form. So the form on the previous page, x plus iy, this is referred to as rectangular form because it's kind of like a vector. It's giving you components, the real component and the imaginary component. It's possible to express that in terms of r and phi instead of x and y, and that's done through this Euler's relation. So if the magnitude is r, and I take r cosine phi, which was our x on the previous page, and I take j times r sine phi, which was our y on the previous page, I can express that as an exponent times a magnitude. So r is the magnitude, and then I have e to the j phi. And this is Euler's relationship. It comes from complex number mathematics as well as trigonometry. And notice in this particular formula, we've used the notation of j instead of I. Now, Euler's formula is extremely important for getting a basic in-depth understanding of, first of all, easy ways to manipulate complex numbers, and secondly, how to deal with these AC currents and voltages mathematically. So keep this equation in mind as we go through the rest of the lecture. Now, the absolute value, also referred to as the modulus or the magnitude, sometimes as the amplitude of a complex number, is basically just found using the Pythagorean theorem. So the magnitude of z, which is written with an absolute value sign, is equal to r, which is the length of the vector in a complex plane. It's the square root of x squared plus y squared, so square root of sum of the squares. The phase angle is basically the inverse tangent of y over x, and you can look back at that figure in the previous slide to see where that relationship comes from if you can't visualize it without the figure present. So from trigonometry and Euler's formula, we can write a complex number in polar form. If we have a magnitude of 1, basically Euler's formula says that some e to the I theta is cosine plus I sine theta. And you probably remember this from your high school Algebra 2 or pre-calculus class. Now, likewise, we can use a notation that says take the real part to express the cosine function in terms of the exponential. So we can say that cosine theta is the real part of e to the I theta. So this is why, because the cosine function is the real part of this complex number, this is why in electrical engineering we always work with cosine functions. So if you're given a voltage or current that is a sinusoidal function, we always convert that to a cosine function because then we can use this little equation right here, which is going to end up being key to how AC circuits are solved. All right, so back to our cosine function, back to our voltage. So we had this V naught cosine of omega t plus phi, and in this case our entire angle, this omega t plus phi is our entire angle, and it does vary with time. So we're going to express this cosine function as the real part of e to the j times the angle, but in this case the angle is the entire omega t plus phi. And then using the properties of exponents, this expression can be written as two different terms, e to the j omega t times e to the j phi. So if you don't remember that property of exponents, you might want to look that up, or I can give you a reference to a Khan Academy video or something similar that discusses this. Now, in an AC circuits application, the frequency term, so that would be this omega t term, in the above equation is going to be common to all currents and voltages in the system. So what you do when you solve a circuit is you know that every current and voltage in the circuit is going to have this cosine of omega t thing, and it's going to be the same. So we're going to ignore it, which means we're going to take away the time variation. And so what we'll have left is we'll have this V sub 0, which was the magnitude, e to the j phi, where phi is the phase. So the unique information in an AC voltage, in an AC circuit, is the magnitude and the phase. So if we can solve for the magnitude and the phase of every voltage everywhere, then we can just convert that back to a cosine function by adding an omega t plus phi inside the cosine and placing the magnitude in the front. So it is a way to simplify the solution, take us out of the trigonometric domain and the transcendental equations associated with that and into just complex number math. So we can, by doing that, we express the voltage in what we refer to as phasor form. We call this a transformation. We call it a phasor transformation. The other thing that we do is temporarily we drop this real notation, knowing that it's there and it's in the background, but it actually takes up quite a lot of space to have it there. So we just are going to work with only the e to the j phi part, and then we'll add the real part. We'll add the function, the act of taking the real part back when we get ready to do the reverse of the phasor transformation. So basically, here's what the phasor transformation looks like, and this goes both ways. So in other words, if you're given V naught cosine omega t plus phi, you can transform that into the phasor domain by taking the magnitude and the phase and just directly writing the expression V naught e to the j phi. And in electrical engineering, we abbreviate e to the j phi with this angle phi notation. So we take V naught, we take V naught and we take phi, and we just write those in phasor notation. And notice here that the reason this is a transformation is that the cosine function has gone to the exponential. We've dropped the real notation and we've dropped the omega t part. So we need a different way to represent that. So we use this capital V with the little squiggly over it to represent that we're now talking about a phasor voltage, not a time domain voltage. So what I really want you to get out of this class is how to take this cosine expression and convert it to this phasor expression, which as you can see is very trivial. And then we'll look at doing a little bit of mathematics on cosine functions by doing this phasor transformation and then transforming back. You'll see a lot of this in other classes. Immediately what comes to mind is circuits 1, circuits 2, and fields 2. All right, so as an example of the kind of thing that this will help you do, and we'll actually work this example out in another video so that you can see all of the steps. But here we have the steps summarized. So for example, let's suppose you have an expression that looks like this. So we want to find the sum of these two voltages. Now notice that first of all, in order to be able to do this, omega has to be the same for both. So in this example, omega is 2 in the first expression, and it's 2 in the second expression. And then missing from this, PowerPoint was giving me some issues. The 30 and the 45 are in degrees. All right, so given this expression, the first thing you do is you convert to the phasor domain, and then you express the phasor as a complex number in rectangular form. You then do the math, and then you convert back to the time domain, and this enables us to take the sum. So in the next video, I'll illustrate an example where this is done.